Hey guys, Miss Peterson here, and welcome to our Physics in the Universe lecture on sound waves. But before we get into it, I want you to stop. I want you to listen. And I want you to think about how the sound wave is getting to you right now. So, right now, you are listening to my voice coming out of your speaker. Your speaker is taking the electrical input from the computer, from the stored sound voice of this video, and vibrating your speaker. And that vibration is pushing on the air molecules near your speaker, which are pushing on the air molecules closer to you and closer to you. Through that wave is moving through the air until it vibrates your eardrum. Okay? And with that, I am able to get an idea from my brain to your brain through the amazingness that is sound waves. So, what is sound? All sound is a longitudinal wave, okay, created by vibrating objects. In this case right now, it is my vibrating vocal folds, okay? When you clap, you hear the vibrating air molecules that you're forcing to move between your hands, okay? If you stand by a bass speaker, you will see it vibrate. An important thing to know is that sound waves travel in all directions from their source, which is why you can hear me whether I'm facing you or whether I'm sitting backwards, okay? Maybe not as well, but my sound waves are traveling and they are bending around my face until they can get to my speaker. Now, also, sound, that is not true. Sound does tend to travel faster through more dense materials, okay? And the speed of sound in air is 343 meters per second. Yep. Okay, cool. So, how do we describe a sound wave? Well, it'll help if we look at some. So this is a virtual oscilloscope. What it's doing is it's graphing my sound wave as I'm creating it. Okay, so I want us to notice some things about this sound wave. First, what is the difference between when I talk really, really quietly versus when I talk loudly? Okay, what changes about the sound wave? Did you notice? Okay, there we go. So, what characteristic of the wave is the volume? Okay, volume. Okay, cool. Now, let's look at another way that we talk about sound in terms of pitch. Okay, I'm going to try to make a high-pitched sound like wee, woo, ee, woo. Okay, that's not a singer, not the best, but hopefully you get the general idea. Now let's go ahead and try a low-pitched sound like ooh, oh, ooh. So, high, yee, high, versus low. What characteristic of the wave do you think pitch is? So, how do we describe sound waves? Now, we still describe sound waves by the same things that we describe all waves by. We just have different words for them that are specific to sound. For example, frequency is just the pitch. Okay, a higher pitch typically means a higher frequency, which means a lower wavelength. The range of human hearing, we can hear sounds from 20 to 20,000 hertz. Okay, I highly encourage you guys to check your range of human hearing. There's a cool video I'll link in the description about it. And to give it a little bit of context, middle C on a piano is a note that has a frequency of 262 hertz. Where volume is the amplitude of the sound wave. And this is why sound waves tend to get quieter as you go away from the source, and they're loudest closest, is because as those waves travel, they tend to lose energy and lose amplitude. Okay, cool. Okay, cool. So let's look at an example. We see a flash of lightning, and then 3 seconds later, hear the thunder. So our time is going to be T is 3.5 seconds. We're talking about a sound wave, and as we said on the previous slide, sound travels at 343 meters per second in air. And we're looking for how far away that sound wave is. So we're actually looking for a distance x. So we have velocity, time, and distance. So we can use velocity equals distance over time to solve for that distance. If we're solving for just that distance, I will multiply both sides by time. So my equation becomes distance equals velocity times time. And if we plug in our variables, we have 343 meters per second times 3.5 seconds, which tells you that the storm is 1200.5. So I would probably just round and say 1200 meters away. Okay, so if we remember, meters to miles is 1,609. That's about 0.7 miles, about 1 mile away. Yep. Now, typically we say we see the light immediately, but it's a bit of an oversimplification. We know light does take time to travel as well, and the speed of light is 3 times 10 to the 8th meters per second. So how long would it take light to travel that distance? Well, okay, we have our speed. It's now 3.0 times 10 to the 8th meters per second, and then we know our distance, that 1,200 meters. Okay, and we're looking for time. So if we look at this equation again, if we're solving for time, it will actually become the distance divided by the velocity. Okay, starting from here, we're looking for time. So we would divide both sides by the velocity to get the equation that time is the distance divided by the velocity. So plugging in our numbers, we have 1,200 meters divided by 3 times 10 to the 8th meters per second, which gives us a time of 0.000004 seconds. Okay, so 4 times 10 to the negative 6 seconds. To put that in context, that is 1,000th of a millisecond, so a millionth of a second. So yeah, we can say we see the light pretty much immediately. Now, one other thing I wanted to tell you about waves, and that is the Doppler effect. So if a wave is in place, okay, it's just going to send its sound out in all directions. But that changes when the wave is moving. If the wave is moving, what ends up happening is the sound waves get compressed in front of it. They look like they have a shorter wavelength and a higher frequency. Where behind the wave gets stretched out. It looks like it has a longer wavelength and a longer frequency. So that's why you hear the as the ambulance goes by, because of the Doppler effect. And I'm going to go ahead and see if I can demonstrate it and if you guys can hear it. So this is what this speaker sounds like. Hopefully you can hear that it's just one even flat tone. And now I'm going to swing it over my head, and I'm going to hope that you guys can pick up the changes in that frequency as it comes toward you and away from you. So that's the Doppler effect. Okay, cool. Okay, cool. There's a lot more interesting stuff to learn about sound, so I highly encourage you guys to check out the linked playlist in the bottom for even more cool sound things.